Alright, chemists, in this lesson we're going to look at salts. Many people talk about salts as if they are the products of a neutralization reaction, which is essentially true, but that's misleading because it makes us think that salts are always neutral. And that is not always the case. It depends on what they come from and what they can do when you put them in water. The best definition of a salt is that they are the product of an acid-base reaction. And many times salts can have acidic or basic properties, and they're not always neutral. If they do, that means they're weak acids or bases for the most part, and we can treat them the same way we treat weak acids or weak bases. So what we're going to do today is learn how we figure out if they're acidic or basic or neutral, and then just look at how we calculate concentrations of ions when you have a solution of one. First, let's review what you might have learned in an introductory chemistry class by drawing the product of a salt from an acid-base reaction. We'll choose the simplest acid-base reaction in the world, hydrochloric acid plus sodium hydroxide, to give sodium chloride, and in this case, water. Now, that happens to be the reaction of a strong acid and a strong base, and when you have a strong acid plus a strong base, you do get a neutral salt. That's not necessarily why the salt is neutral, but it's a good trick to remember that it is neutral when you make it. So let's start by just see if we can figure out what acid and what base would produce a couple of other common salts. Let's say I wanted to make ammonium bromide, sodium fluoride, and ammonium fluoride. Hit pause and see if you can figure out what acid and what base would be used to make each of those three salts, and then come back and check. Okay, let's see how you did. For ammonium bromide, we're going to use hydrobromic acid and the weak base ammonia. Now, maybe you used ammonium hydroxide and then you added a water molecule to the product side. That is still okay. Ammonium hydroxide is just our way of saying ammonia in water in the first place. So they're essentially the same thing, the way we write them out. When you have, in this case, this is a strong acid and a weak base, so we still have a strong acid, but now we have a weak base, and that is a trick for remembering that the salt that you make from that is acidic. Let's check the other two. Sodium fluoride, it'll be just like sodium chloride, but we're going to start with hydrofluoric acid. Treat that with sodium hydroxide. That means you'll need another water molecule on the right to balance. Now we have a weak acid plus a strong base. And here the trick is that gives you a basic salt. So strong plus strong cancels each other out. You get neutral. When you have strong acid plus weak base, the acidic part predominates. When you have a strong base plus a weak acid, the basic part predominates. What about the last one, ammonium fluoride? Well, ammonium fluoride comes from the weak acid HF and ammonia. So we have weak acid plus weak base. Now, if you're guessing neutral, that's a good guess, because just like strong plus strong cancels them out, but weak plus weak does not cancel each other out. We actually need more information. So this is the one we're going to focus on the most when we get to them today. The reason salts are acidic or basic is not because of where they came from, but what they actually are when you put them in aqueous solutions. They're a cation and an anion, and all cations have the potential to be acidic, and all anions have the potential to be basic. So these things actually have K values, which means we need to look up the K values. The Ka for ammonium ion, if you look it up, it has a value. It's 5.6 times 10 to the minus 10. That's tabulated. And then there's also a Kb for the anion. The Kb for the fluoride is 1.4 times 10 to the minus 11. So they're actually pretty close to each other if you look at those orders of magnitude. But the Ka is a little bit bigger. Well, actually it's an order of magnitude bigger. So in this case, we have a Ka that's bigger. And when the Ka of the cation is bigger than the Kb of the anion, that's when you have an acidic salt. If the Kb was more significant, that would be a basic salt. And in the rare cases when they're pretty much exactly equal to each other, that's when you have a neutral salt. And that's actually true for all the situations we just went through. But most of the times, one of the K values is so much larger than the other, or so much smaller than the other, that it's basically insignificant. You can think about it. If you look at ammonium bromide, the Ka of ammonium is 5.6 10 minus 10. We just said that. What's the Kb of bromide going to be? Well, because bromide comes from a strong acid, it's a very small number. I don't even know what it is, but it's infinitesimally small, that the ammonium ion has got to be a larger number, even though it's small itself. Hence, we get an acidic salt for ammonium bromide. So this top part is just a trick to remember the properties of the salt, but it's really the ions that we make that show us what that thing does. So let's practice that. Let's look at a couple of examples and see if we can figure out, are they acidic or basic or neutral? And then we'll even show why they're acidic, basic, or neutral. Starting with sodium acetate. Sodium acetate is NaC2H3O2. And if I try to think about where it would come from, the cation would come from a hydroxide-containing base, and the anion would come from the protic version of this anion. So that's sodium hydroxide plus acetic acid, and that would give me sodium acetate, NaC2H3O2, and then in this case I have a water molecule, and if I label what's what, sodium hydroxide, that's a strong base, acetic acid, that's a weak acid, so my trick tells me that the strong part predominates when one of them is strong, so therefore sodium acetate should be basic. But the reason it's basic, why, what happens, is again because of the ions that are involved. The sodium ion isn't doing anything. It's a spectator, just like it was last semester. But that acetate ion is the conjugate of a weak acid, so it has the ability to do stuff. So if I write acetate and show it by itself with water, there's actually a reversible equilibrium that has a pathway of having acetate take an H, and then you're left with acetic acid. And more importantly, the water molecule has become a hydroxide. And that's why this is basic, because the anion has the capacity to create hydroxide. That's what makes salts not neutral, because they either have a way of making hydroxide or of making hydronium ion, aka hydrogen ion. So, try that for ammonium chloride. Is it acidic, basic, or neutral? What acid and what base combine to form it? And then once you think you figure that out, what actually happens? What ion reacts with water to split water into a hydroxide ion or a hydronium ion, if that's applicable? Okay, let's see how you did. First of all, I need the formula. Ammonium chloride is NH4Cl. This is going to be really similar to the ones we did up above. We did bromide and fluoride, same kind of thing. But this is hydrochloric acid plus ammonia. And that will make the salt, ammonium chloride. Thinking back to what's strong and what's weak, hydrochloric acid is a strong acid, ammonia is a weak base, so I would predict that the ammonium chloride salt is going to be acidic. That's just based on the trick. Now, what happens is based on the ion that does something with water. Once you figure out if it's acidic, basic, or neutral, there's even another trick that you can use to figure out which ion is the one that's doing something. Basic salts have an anion that's going to do something with water. Acidic salts have a cation that's going to do something with water. So here, it's the ammonium cation that will react with water. You'll have an equilibrium that actually turns ammonium into ammonia, and more importantly, the hydronium ion. And that's the key. There's a way of making hydronium. That's why this is acidic. That's the whole reason. Remember, acidic simply means you've got more hydronium ions, and here we're creating a pathway to make them. Chloride is doing nothing. Chloride is a spectator ion. It's the conjugate of a strong. Okay, so that's an introduction to that. Now let's look at some more challenging examples. These three salts, all three of them come from the combination of weak plus weak. So we actually need to look up some reference values in order to figure this out. So the first one is ammonium acetate. I'm going to write the separate ions, ammonium ion and acetate ion. So if I tried to use our shortcut trick that we did in the beginning of this lesson, this would come from ammonia and acetic acid, which is respectively a weak base and weak acid, so I need more information. So we need Ka and Kb values. The Ka of ammonium, we actually have it from up above, 5.6 times 10 neg 10. The Kb of acetate happens to be 5.6 times 10 to the minus 10. Yikes, they are equal to each other. That is a coincidence, but it's true. And therefore, ammonium acetate is a fairly neutral salt. By the way, it's a good time to interject. Maybe I don't have a Kb table, and I only have a Ka table. So let's make a note off to the side. For conjugate pairs, the Ka times the Kb is actually equal to Kw. In other words, maybe I have the Ka of ammonium and I need the Kb of ammonia. That's a conjugate pair, and the product of those two will be equal to Kw, 10 neg 14, at 298 Kelvin, but when we're getting one or the other, this is a perfectly good temperature to use. So maybe the tables you have don't always have both sets of values. That's okay. If you have one, you can indirectly get the other. If you flip ahead a few more pages in your own workbook there's a nice comprehensive table of K values for acids and their conjugate bases, and you can see they're written side by side to each other. Here's the hydrogen sulfate ion, 10 to the negative 2. Here's the sulfate, 10 negative 12. And there's a good example that proves exactly what we just said. Ka of the acidic part times Kb of the basic part equals 10 to the negative 14. Okay, let's look at a few others just to finish this up. Here we have ammonium yet again. Ka is 5.6 times 10 to the negative 10. And then the anion cyanide, anions are basic, so this is a Kb value, happens to be 1.7 times 10 to the negative 5. So we just look who's bigger. It's the Kb, so the cyanide is the more significant ion, so this is basic. When the anion wins, it's basic. When the cation wins, it's acidic. Lastly, let's check aluminum and sulfate. Sulfate has a Kb we just saw a moment ago, 1.0 times 10 to the negative 12. When you look at aluminum, it might be hard to find it at first, but aluminum is acidic because of its ability to form a complex ion. There is what's called the hexa-aqua aluminum ion. That's just an aluminum cation surrounded by water molecules, and it's actually the water molecules that are the source of H+, but it still has a K value. It's 1.2, 10 to the negative 5. So the Ka of aluminum is 1.2, 10 to the negative 5, much bigger than the Kb of sulfate, so this is acidic. Alright, so that's how we determine if a salt is acidic, basic, or neutral. What's left is to calculate what actually happens when we have a solution of one of these things. So let's say I have a 0.3 molar solution of sodium fluoride and I want to know its hydrogen ion concentration. Well, what's really happening in a sodium fluoride solution is I have sodium ions and I have fluoride ions. And both of them have the potential to react with water. Now we should know sodium fluoride, based on what we just went through, is basic. The sodium cation is not doing anything with water, but the fluoride anion has the ability to create HF and hydroxide. Again, that's why it's basic. Well, if I have an equilibrium that creates hydroxide, that means there's some Kb expression I should be able to write for this, and it's got some numerical value. Aha, they give me the Ka of HF. That's the conjugate acid of fluoride. So I sort of know the Kb, it's just indirectly via Kw. And I can use that because I can set up an abbreviated Rice chart for this equilibrium, like every other equilibrium we've ever done. We are in 0.3 molar sodium fluoride. There's 1 to 1. So that 0.3 also applies to just the fluoride. So I'm going to write 0.3 minus X underneath the fluoride. I'm going to write X underneath the HF and X underneath the hydroxide ion. And then I can say Kb is equal to, well, it's equal to Kw divided by Ka, which is 10 to the negative 14, divided by the given Ka, 7.2, times 10 to the negative 4, and I'll set that equal to x squared all over 0.3 minus x. And as we've done many times, this is a weak acid with a small dissociation, so we're going to assume that it doesn't dissociate much compared to the original 0.3 molar and set this roughly equal to x squared divided by 0.30. That way we don't have to worry about solving a quadratic. So here I have, or at least a more complicated quadratic. So there's our mathematical expression. We can just do the math. You solve for x after rearranging. You get 2.0 times 10 to the negative 6. And I'm going to remind myself at this point what x is. X is an abbreviation for hydroxide. It's a Kb value. So I always like to write that at this point. That's my molarity of hydroxide. And now I need the pH. The pH is the negative log of the OH concentration. Of the H concentration. And what I have is the OH concentration. And then I have to subtract that from 14. So it's 14 minus the negative log of what we just solved for. And I can do all that on the calculator and just write the numerical value. So in this case, I get 8.31. And it's not a bad idea to just do a little self-check, see if it makes sense. 8.31, it's basic, and it should be. That's good. Also, this is a weak base because it's a basic salt. Basic salts are just weak bases. Acidic salts are just weak acids. Alright, there's one more to try. I'd like you to hit pause. Here's a 0.01 molar solution of aluminum chloride. They give us the Ka of the aluminum ion. So you can figure out what you do to get the pH of that. Okay, I'll start by doing the same thing we did up above, and I'll write the ions that we have. We have chloride, which with water isn't going to do anything. That's a spectator ion. The aluminum ion is actually not a spectator, and that's because it exists as this species. It's this hexa-aqua aluminum ion, so it can act as an acid. And I'm just going to write the equilibrium that goes with that Ka value. We did this in the first lesson. Of the 6 water molecules, one of them will donate an H, so you'll get the 2+ charged aluminum species with 5 water molecules and an OH, and then just a lone H+. That's what the Ka expression looks like for that species. So I have 0.01 molar minus X of the starting compound. I have X of its conjugate base, and I have, most importantly, X of the H+. And that's a Ka, so I can just use the given Ka. Ka is 1.4 times 10 to the negative 5. And I can set that equal to X squared all over 0.010. I'm just going to go right to that. We know we're going to assume this X is negligible. And notice the Ka that's given is exactly the one I need. I don't have to do any Kw calculations because I'm working with the acidic part anyway. In the previous part, in the previous problem, we needed a Kb value. Not true here. Here we needed a Ka. They gave us a Ka. So I solve for X. I end up getting 3.7 times 10 to the negative 4. And at this point I'll say, what is X? Well, it came from a Ka value, so this is my molarity of H+ ions. And then to get a pH, I simply take the negative log of what I just solved for as X, and it turns into 3.43. Makes sense, because we are in an acidic salt, so our pH should be low. In the lower right, I just have some reminders of common spectator ions that you'll see, which means these aren't going to do anything with water when you find them in salts. If it's got an anion, it has the potential to be basic, as we could see with these. And if it's a cation, it has the potential to be acidic. So that's a good thing to just know when you're looking at K values, which one you actually use. And that's how you solve for the concentrations of things when you're in a salt solution.